So, good afternoon, attendees. We're going to talk about cluster computing today, and that covers from supercomputers down to Raspberry Pis. So I'm Robert Witinger. A lot of people call me Bob. I do engineering consulting work with my company Trex LLC, and I'm also affiliated with ETSU, High Performance Computing Center, where I'm helping to administer a couple campus clusters. So the topic here is cluster computing, and with a Linux focus. I don't know about you, but I hear people saying that Linux has like a 10% footprint, or maybe even as low as a 2% footprint. Well, that might carry some weight in the area of desktop computing, but when we turn over to supercomputing and computing clusters, the the scale is just flipped 180 degrees around, and so it's really a Linux world in the space of supercomputing and cluster computing. And I think in the course of the next minutes, the next hour, I think we're going to see why that is, why Linux is such a close fit to cluster computing. So if you look at the top 500 supercomputer list, the top 500 computers in the world, the last published report was from November of last year, and Linux ran 485 out of the 500 systems. Now, if you add in Unix, that brings in another 13, another 2.6%, and that leaves one machine on the top 500 that is running Windows. So if Linux is running 10% on the desktop and Windows is running 0.2% on the largest computers, I think that we have an interesting Linux space over here in the supercomputer area. There's also one system that's classified as mixed. That Windows system, I believe, is in China, and it ranks down around 300 plus in the 500 list. It's interesting to look at how fast computing performance has been going. This is a logarithmic chart, so a straight line in this chart is an exponential growth. And the red line in the middle, that plots the performance of the world's fastest computer as a function of the year. The yellow line in the bottom charts the other end of the spectrum. That's the performance of number 500. So the top 500 ran in between those ranges. The top dark line is the summation of all computing power in the top 500 list. Now, the current number one computer in the world is the Tianyi 2 in China. That went online in 2013 with 33 petaflops of computing power. The previous number one was the Titan from Oak Ridge National Labs over on the other side of the mountains in Oak Ridge, Tennessee. They held the number one spot prior to that, and you can see that the number one spot has been flipping back and forth between China and the U.S. over the last few years. The the next computer planned for Oak Ridge will be 100 petaflops plus. That's planned to go online, be delivered in 2017. It should be in production use by 2018. So if the Chinese don't do anything, in the meantime, we'll have the number one computer in the world back here in the U.S. So this is what the high end of the supercomputer spectrum looks like. What you're seeing here is a long row of racks, and each rack contains computing modules. What you don't see on this picture is that this is only one row. What you have to do is picture, you can't get it all in one photograph. You have to picture a basketball court sized data center with row after row after row of such cabinets. So that's what the largest computers in the world look like today. Now we got there through a path. If you look at the computing architecture historically, we started out with small systems. The Cray 1 from 1975 was designed by Seymour Cray, who also designed the Control Data System 6600. He spun off his own company and based it in Chippewa Falls, Wisconsin, and came out with this machine, the Cray 1, in 1975. Now, this architecture had a central processing unit. In the case of the Cray 1, it was a pipelined central processing unit. The idea was make a CPU go as fast as you can and then surround it by memory. So in order to do that, they used pipelined instruction architecture. And then they went out to get memory and bring data back from memory. The limitation is the speed of light. If light goes and electricity goes 1 foot every nanosecond, then a 12.5 nanosecond clock rate is going to mean that you don't have very many feet of distance to work with. And that's why what you see here is a circular arrangement so that the wires didn't have to travel so far to get out to the memory and then come back to the central processing unit. So that that created a limitation in how much hardware you could put in one space. If you tried to make it bigger with this architecture, you'd be slowing the machine down. Cooling was also an issue because you've put a lot of high-powered equipment, 115 kilowatts of power, generating heat that had to be dissipated. So what did we get in 1975 with the Cray 1 in terms of performance was 80 megaflops per second. Now, by comparison, we can buy these today. You probably all have one. Raspberry Pi version 2 has 4 cores, and someone has done a LinPack benchmark on this machine, and we found that it has a 1 gigaflop performance. So that means that one of these Raspberry Pis has the computing power of 8 Cray 1 supercomputers. So we live in an exciting time when a $35 piece of hardware can compete with the world's fastest computer in 1975. So that's a little perspective. But then we skipped to a different architecture, and this is where Linux starts to come into the game. The idea was, instead of trying to build the fastest machine in a centralized architecture, let's use slower machines, but lots of them. And so the distributed architecture came about. This was not the first distributed architecture machine, but it was one that was successful. In 2004 timeframe, the IBM Blue Gene supercomputer had achieved 70 teraflops of power, and it was leading the Type 500 list for a little while. So the idea of the distributed architecture is smaller processors, very large numbers of them, and then fast networking so we can get the data back and forth. We're not dealing with memory data coming into a central processing unit. Now we're dealing with packets of information. So the software architectures were a little bit different. Now you're dealing with subdividing a task into n number of smaller problems. You give them to the computing units, collect the results, merge them back together. So this is the architecture that began in that time frame, and it has served us well up to the present point in time. Now, Linux played a role in the development of this distributed architecture, and that role goes back to the 1994 timeframe with Thomas Sterling, Donald Becker. Both were NASA employees. They were funded to do a project that developed a high-performance computing HPC cluster using commodity off-the-shelf systems. The idea was buy things that are cheap, network them together, implement some message passing between the nodes, share the file system with NFS. It was all open source software back then. And each system is usually identical, running the same operating system, same configuration, although there are some heterogeneous implementations as well. This project, the Beowulf Linux Cluster Project, was highly successful, and it quickly spread throughout the various NASA research organizations, and then and made its way into academic and research organizations within a year. So this is what made HPC affordable for scientific communication, scientific computing. So the elements of a Beowulf cluster, or we just usually say cluster right now, are these. A cluster has compute nodes. The more of them, the better. Networking, we can have a wide range of networking speeds. The faster the network interconnect, the better. We can implement very inexpensive interconnects between systems using 100 megabit Ethernet or 1 gigabit Ethernet. On the other end of the spectrum, the new system coming into ORNL will use an InfiniBand interconnect that will be capable of supporting 23 gigabytes per second. So that's the other end of the spectrum. The other elements, we usually have a shared home directory. All nodes are looking at the same files in your home directory, and NFS works very well for that purpose. And then we need message passing. So a compute node needs to be able to receive arrays of data from other nodes and return their results. This is what a middle-sized cluster looks like. I mentioned that I'm working with the group at ETSU in Johnson City. This what we have here are two clusters. The one on the left, the two racks on the left, is the oldest of the two, and that's a Dell cluster. And the two racks on the right are from Hewlett-Packard. It's a newer cluster, about 4x the performance of the one on the left. So that's what that's what a typical campus cluster would look like. And if we open up one of the doors and we look inside, you'll see that they're typically blade oriented, so you can pack a lot of hardware into a small amount of space. You still have heat problems, and you still have power problems. We draw 80 to 90 amps from a 208 volt three-phase service. Okay, 24/7. So these things they're not cheap to operate, even if you're just counting the power bill. So haven't you always wondered what version of Linux is running on these systems? Well, in China, they did a Linux version that they called Kylin, and this is the version that's running on the Tiana 2 system. There are a number of other distributions, cluster Knoppix, based on the Knoppix distribution, and some of these are historical because they're no longer maintained. One alternative that a surprising number of organizations are using is actually to do your own work rather than using a cluster-oriented distribution. Pick up a standard distribution and then adapt it to your purposes. More work, but you can also fine tune, and so there are some good reasons for doing that. There are various commercial Linux distributions. IBM has one that they sell with their products. Cray has one that they sell with their products. My favorite is called the ROX cluster distribution. And the ROX distribution is intended specifically for HPC clusters. It was created at the San Diego Supercomputer Center in the year 2000. It's totally open source. And it is currently, last I looked, it was running on clusters with a little over 8,000 nodes. And of course, you can run it on any cluster as small as you want. It's actively maintained. The current version 6.2 was just released last month, and we're just in the process of installing that version on the ETSU system right now. So ROX is based on CentOS, which in turn is based on Red Hat Enterprise Linux, but it adds essentials necessary for operating a cluster. The message passing interface that we mentioned, it has a very nice cluster-aware installer. So you're installing on both a front-end node and also on all of the computing nodes in one well-organized installation. Quickstart integration, we'll talk a little bit more about Quickstart later. They have a monitoring package called Ganglia. It's an open source monitoring package. Presents a nice single page view of nodes in the system, who's up, who's down, and the loading on the various nodes. And scheduling, we'll talk more about scheduling in a couple minutes, but scheduling is real important if you have scientists and researchers who like to run programs that will use 100% of your CPU for 2 weeks. Then you might have some other users who would also like to be running 100% of the CPU for 2 weeks. So it's important to have some sort of a scheduling package to keep that under control. Now, if you're, I expect that there are probably 3 groups of people in this room. There are some people who are currently doing system administration on clustered systems, and there are probably some people who are interested in cluster computing, maybe doing it with commodity systems like Raspberry Pis, and but there are probably also some people who are looking at the job opportunities, and they've noticed that, there are quite a few job opportunities for system administrators with Linux experience and some cluster experience. So I've made a list. If you're in that category and you'd like to see yourself as becoming qualified to compete for some of these jobs, this is just a quick list of the topics that you would want to familiarize yourself with so that you succeed in the job interview. So scripting or point and click, that's an issue. In this group, I don't think we need to talk about that issue a lot because I think you understand the value of scripting. But there are other groups that think that point and click administration is real cool. And so we need to talk about that a little bit. How do you keep thousands of nodes in sync? A non-trivial task, but one that needs to be brought under control. Now you have a user community, people who are going to be needing training, support. You need a strategy for supporting a user community. That should include some quick start documentation so that users can come up quickly without a lot of hand-holding from you. Uptime is important. What if you have 500 nodes and the probability of failure of one node is X? Well, now the probability of getting a failure in your system is 500X. So you need to have a strategy that lets you bring defective nodes out of the system, bring them back into the system without upsetting the production that's going on. Benchmarking is important. Various storage strategies to consider, power strategies, third-party software administration, updates, and then if you have an administration team with only one person, then this one is trivial. But if you're running a large supercomputer, more than likely you've got an administration team. So you need a way to keep the team all on the same page. So that's the quick list of issues. Scripting versus point and click. So if you have a task that you're only going to do once, you want to write a memo. So you're going to call up a word processor and start clicking around on the page, and you click on the print, and now you have your memo written. That's fine. But what if you need to do something twice? Like I want to install an operating system on machine A, and now I want to install the operating system on machine B. The point and click method is problematic. It takes you twice as long because you have to do it twice. And furthermore, you might skip a step or make an error in entering a parameter. So you may not end up with the same operating system on both of those systems. Now, multiply that. What if you have 50 nodes on your cluster? Point and click is out of the question. Not suitable. What if you have a supercomputer with 500,000 cores? So scripted task automation is really the only game in cluster computing and supercomputing. So in my opinion, this is why we don't find Windows running on supercomputers and clusters, because it's possible to do scripting in Windows, but Windows was designed first as a graphical environment, and then scripting was added on top, and Linux was designed the other way around. The first Linux was a scriptable environment, and then later on we added graphical on top of it. Because of that, if you've done scripting in both environments, you appreciate the power that you have in a Linux environment. So how do we make hundreds or thousands of nodes look the same? Doing it by hand doesn't work, so we have to do it in a better way. Now the ROX and the Red Hat solution uses RPM packages and the quickstart installer to solve this problem. So you define what a compute node installation looks like, and remember, all of these compute nodes are running a full-up operating system. They're operating the same operating system. They're all identical usually. So we define what we want by deciding which RPM packages go into it, and then we say Kickstart. And Kickstart is a tool that came out of Red Hat, and it does an installation based on the rules that you've set up on that node. So you can say kickstart all of my nodes, and in parallel, all of your nodes are installed. It can take a minute or two to update. Now another tool that I find I need to use on a daily basis is PDSH. Many of you have probably already used that. It's a parallel SSH program. And here are a couple of examples that show the power of that. So if you had 50 compute nodes and you wanted to issue a command to all 50 nodes, then you do it like this: PDSH. W says, these are the addresses of the nodes that I want to talk to. Here I'm addressing rack number 0, nodes 0 to 49 in that rack, and I want them to run the program Uptime and give me the results. And this is an actual result that came back from our ETSU cluster. And you can see that we get 50 lines back with each compute node running its command. Now, most of this open source software is available in standard repositories. At my home, I have 4 Raspberry Pis. I call them RPi 1 through RPi 4. And they're serving with security camera duty. Security cameras only take 0.1% of your CPU, so I figured, well, okay, I'll just set up a cluster on these spare Raspberry Pis. After all, they're already networked, so it doesn't cost anything to turn them into a cluster. So here we have sending a PDSH command to 4 Raspberry Pis, asking them for their uptime, and we get back the same kind of results. So going through the essentials of cluster administration, we said that community building was important. What we use is a cluster wiki using MediaWiki. So we have wiki pages that we use to communicate information to users. Users can develop their own pages for code exchange. They can share best practices, and we show users some quick starts in each of the languages. So a user can come to the wiki and they have enough information so that they can actually run something in a clustered environment. And then the easiest way to write a program is to have a program that already works, and they can modify it to suit and start to build their own software. So here's an example. I won't spend a lot of time on this, but the slides are available. If you want to run this on your own cluster, if you're implementing a Raspberry Pi cluster, or if you have a larger one. What we have here is an example that shows a Python program using the message passing interface on 50 nodes to do something very simple. Now, we launched that with MPI run, which is a part of the Open MPI package. We tell it how many nodes we want to use, and then we give it a command. In this case, Python, and there's the name of the Python program. That's the command that we want it to run. We have a Python library called MPI4PY that knows how to support the Open MPI. And using that, we can then write our program. Now, get rank is the name or the number of the compute node that we're talking to. So we asked for 50 compute nodes, so we get rank ranging from 0 up to 49. So the program itself is written much in the same way as you would see a multiple process program that forks additional processes or threads. In this case, we're forking onto another compute node. So remember now, each node is going to be executing the same program at the same time. That program that was in your home directory, we've NFS shared the home directory so that all nodes see it. And when we run it on all nodes at the same time. Now, the node knows its rank number. So we say if I'm rank 0, then I'm going to be the master and the data organizer. If I'm not node 0, then I'm going to be a computation element. I'm going to receive my little packet of work. I'm going to do my work, and then I'm going to return the result. So you can see how that works. We just use standard Python to create an array of 100 floats. And then inside that array, we put a value, and then we use MPI to send that array to all of the other compute nodes in the system. Now, if you're not node 0, then you're doing the opposite thing concurrently, where you create an empty array of the same size, and then you tell MPI that you want to receive the contents of that array into it. And then after you've exchanged MPI communications, then you do your work and send the result back. So here we're printing rank number, and the last element is our simple computation, where we're taking the first entry in the array, multiplying it by pi, and returning the result. So it's a real simple application, but you can see that the concepts can be extended arbitrarily. So when we run it, yes. Okay, so the question is, does each node get a different value? It can. It's up to you. Now, in the example, in this example, node 0 is creating one array that it's sending to everyone. And that's common. But you could code this if you had some other way to partition the program. If you were doing a galaxy collision, for example, you'd want to send a piece of the galaxy to node 1 and another piece to node 2 and so forth. So we... Right. So in that kind of a program structure, then node 0 would send individual packets to specific nodes, and then those nodes would send individual packets back to node 0 for assembly, and then it would combine those and reorganize the galaxy and send out the next iteration of it. So job scheduling, we touched on that. How do you control the computing hogs? And with scientists and researchers, they're all computing hogs. They'll take all the computing resources that you've got. If you have a Titan or a Tiana 2, they'll use it. And it makes sense, because if you have a simulation that that has some resolution, if you increase the size of the resolution, you increase you're doing a galaxy simulation. Instead of taking an increment of one light year, you go down to 1/10 of a light year. The result is going to be more fine-grained and better. So the applications tend to grow until there's no more computing power left. It's the nature of computing research. So you've got to have a strategy for controlling computer hogs, and that strategy involves a scheduler. And so when if I go back and I look at this, when I say MPI run, I want 50 nodes. I'm really telling this to the scheduler, and the scheduler will try to work it out for me. So the ROX distribution comes packaged with what's called Grid Engine or SGE. How much time do we have left? Okay, good. So it's called Grid Engine or SGE. I'm going to try to leave minutes at the end here for questions too. So this is open source software, and it does a good job of allocating resources. You can specify what I need. My project needs 1 GB of memory on each node. I need 200 nodes, and when those resources become available, then your job can start. That sort of thing. Okay, another issue is uptime. You want to maximize uptime, but you also have to deal with the reality that you have a high probability of failure when you have such large systems with such large component counts. So for uptime, there are some tools that help us. The Ganglia program that I mentioned before comes packaged with ROX distribution. It's open source. It gives you a single web page with status of nodes. You can see instantly how your system is loaded. If you have any failures on it, you can see that immediately. SNMP is a good tool. You'd like to. Oftentimes, you don't have immediate access to these systems. You might be administering them from remote locations, so you'd like to have a KVM so that you can access the system remotely. You'd like to be able to remotely power cycle individual nodes, and then watch the BIOS come up. You'd like to be able to do all of that remotely. Node kickstarts with concurrent with operations. This is really a cool thing if you can implement this. Imagine that you have your scheduler running, SGE. Your scheduler is taking jobs from users and allocating those jobs to the available compute nodes as they become ready. What if you injected into this system a job that says, I have a new set of RPM packages that I want to include in the configuration. I want that to be applied to all nodes. So I'd like to kickstart a node. I'm going to do a fresh installation, take it all the way down to the metal, bring it up with a new configuration. Well, you give that to your scheduler as a job. The scheduler goes around and finds nodes that are becoming idle. They are idle now, or they're becoming idle soon, and it declares them not active for new jobs, and it'll send them a kickstart. A minute or two later, that node is up to date and joins the mix. Meanwhile, other nodes become free, and so in the course of not a lot of time, maybe 10 minutes, 20 minutes, you've reinstalled all nodes without ever interrupting any of the jobs that are going underway. It's a real powerful thing, and users appreciate it because you don't have to take your system down and stop that program that has been running for a week and a half out of its 2-week lifetime. So benchmarking is is important. The LinPack benchmarking is used for computational performance in the top 500 ranking. And I also like to use the Bonnie++ benchmark for disk I/O. If we're playing with different storage configurations, we'd like to be able to have a means of measuring read and write performance into disk. So power strategies. Most systems that I'm familiar with are running backup power, UPS power on front-end nodes and on critical storage systems. They typically don't take a lot of power, so backup power is feasible for that. But they're running directly on the mains for the compute nodes. If you have hundreds or thousands of systems running on kilowatts of power, the cost of the UPS would be quite large. At ETSU, we generally see maybe one or maybe two power outages in a year, and the impact of that is not large enough to justify the cost of a UPS. And we've asked other organizations, and this seems to be a common practice. Typical power configuration I mentioned was 208 three-phase. It's interesting that ORNL with the Titan installation, they went up to 480 volt power in order to reduce the diameter of the copper wiring that they needed. And they claim that they saved $1 million in copper wire cost by making that design change. That's right. The observation was we have the same numbers of wires, but the amount of copper in those wires is smaller. $1 million in copper. So, third-party software administration. Okay, in a perfect world, we would have all of our software located in a repository, and we would yum install everything, and we would be so happy because the QA organizations will have worked out the issues, and we will have a consistent system that that we're happy with. That's the perfect world. Now, in the real world, in this space, you've got a lot of scientific software that's sometimes old, sometimes even older, and a lot of this software, and little of this software has been merged into the repositories. So you are faced with user demand for installation of third-party software. There's a program called NWChem, which will simulate chemical molecule dynamics. And NWChem is a bear to build because it relies on libraries which are generations older than what is installed on your system. So you need a strategy. It would be wonderful if you could just say to users, well, we're only going to use stuff that's in the repository, but that's not the real world. We have to have a way to deal with third-party software administration. Now, if you're on one system, you'll do you'll do a tarball installation and you'll be finished. But if you're on a system with hundreds or thousands of nodes, you have to really think carefully, how am I going to do this so that all of my nodes are in sync? So there are some tools for that. The ROCks idea is to use RPMs for everything. So if you build a third-party package, you do it as an RPM. ROCks gives you some tools that make that pretty painless. one of the things that I like to do is I'll make an RPM of the user local directory in its entirety, and then I'll include that RPM in the Kickstart package. So now anything that I manually build into user local, I'm assured that that will be available on all nodes. That's kind of a quick solution to this that has worked out pretty well. Oak Ridge National Labs has done some good work on something that they call software tools or SW tools. There's a later version of it called Smithy. It's on GitHub. And SW tools is basically a build frame for third-party software. So you can specify the rules for a build, and then the build frame will accomplish that build for you. So you can get it right once, and then when you need to come back to it again next year, while you're adding in more software into the mix, you don't have to go back and revisit it. So that's a strategy that has worked out well for them. Now, then lastly, we want to talk about how to keep an administration team staying on the same page. So if you have a Raspberry Pi cluster with four RPi 2s and you're doing the administration, then this task is easy because you're the only administrator and you have everything in your head. But if you're in a campus computing environment, or even worse, if you're administering a system like the Titan, then you need to be a little bit more organized because you've got a team of people who are involved in administering that system. Here are a couple things that I do that have really given a lot of leverage. First of all, and this is so simple, we have a text file. It's an admin journal file that we keep in the root directory. So all admins have access to it. We call it admin log. And this is it's a day-by-day chronology of how a system is evolving. So if you're an admin on the system, you make a change to some file, or you install a piece of software, then you make a note in here, and all your fellow admins can see the note. We also put in how-tos. If you've spent 15 minutes figuring out how to do something and you've worked out all the parameters to the command lines to do something, just drop a note in here, tag it with how-tos. We can grep the admin log for how-to, and you can save your colleagues some time. And the second one, and this sometimes is helpful, is to, whoops. Okay, there we go. Use a version control tool on your ETSU directory. So we use Mercurial basically because it's so easy to set up. CD to the ETSU directory, say HG init to give it a version control, and then make your initial commit. HG, I'm committing everything with a comment of this is my initial commit. Now, every time one of the administrators changes a file, that's going to be logged in our version control. So if I want to go back and I want to look at ETSU FS tab and see the history of ETSU FS tab back to the beginning, I can do that very easily then. I can see who made what changes. So we're getting close to the conclusion, and the conclusion is, what's next? Where do we go from here? The next level is taking distributed systems into hybrid systems, where we have nodes that are a combination of multi-core CPUs, but also GPUs. So the idea of using like an NVIDIA graphics processor unit as a sub processor underneath the main node processors. That's what is being leveraged on the next systems that are coming out. Titan already is using the concept. The new Summit system that comes in 2017 is using this concept and using it. They're only going to be using 3,400 nodes. So the actual node count in Summit is going way down compared to where they were with Titan, and they're doing that with CPUs and attached GPUs in each of those nodes. That system will have a half of a terabyte of high bandwidth memory that is global and accessible to all nodes. The disk capacity will be 120 petabytes, and bandwidth into the storage is targeted at 1 terabyte per second. The operating system is Linux. It'll be the IBM Linux, and a lot of the software is open source software. And it's so interesting to me how Linux does such a beautiful job of spanning from the most complex high-end systems down to the $35 Raspberry Pi. You can apt get an OpenMPI into your Raspberry Pi if you want to use MPI communications on your own home cluster, and at the same time, the next generation fastest supercomputer in the world is going to be using the same open source software to accomplish its MPI communications. Compilers will also be familiar to you. GCC will be available, and they've targeted 10 megawatts for the power consumption on that system. So if you are currently working on a system like this, then I'd like to talk with you afterwards and share best practices. If you're not, then maybe you could build one of these and get your feet wet with cluster computing using Linux operating system. This came from the Raspberry Pi organization, their branch in Switzerland. They put that little mini cluster together with 8 Raspberry Pis. And the slides that I showed are available online. There's the URL for it. And that's how to reach me if you have any email questions. So, open for questions. Yes. Yeah. Well, of course, if a node goes down, and okay, excuse me, let me repeat the question so that we can hear it across the auditorium. What are the question is what are the real-time consequences if we do have a node failure? And a lot of that depends on how the user has structured the software. The application software wants to take a big job and break it down into smaller pieces and send those pieces out and then collect results when it comes back. If a node goes down while it's carrying out that, if the application has the strategy to reissue that job packet to another node, then nothing is lost, and the job is simply re-executed on a different node, and the results come back. Right. Mm-hmm. We had another question over here. Yep. Right. Right. So the good question. What do we use for networking benchmarks? There might be better networking benchmarks available. What we do is DD from dev 0 to dev null over an SSH link. Cheap and dirty. Hyper. Look into that suggestion that Hyper would be a good benchmark for network interconnect. Good. Other questions? Okay, another question? Yeah, Ansible is actually, the question was, what do we think about some of the new configuration tools like Ansible? Ansible is, by the way, included in the ROX distribution. So I know that they're using that out in California at the Supercomputer Center. I personally don't have experience with it, so I really can't comment. But it may have some value, and obviously does have some value if it was included in the distribution. Okay, question. Mm-hmm. The question was, do we, we're interacting with users in somewhat of a support and consulting role, and that is true, but do we also do code audits in order to keep people out of trouble? Was that the question? Yeah. And I think the best answer is no, we really don't. That's kind of outside of, you have to define your scope. Otherwise, you may end up missing high priority items while you're working on lower priority items. User communities, I think, our thinking on user communities is that they like to help each other. So our role is more along the line of providing them with tools where they can efficiently interact with each other. An open wiki that anyone can edit, would be a tool like that. So somebody should be able to post a question, and a dozen people could provide answers. Mm-hmm. Good question. Mm-hmm. One more? Mm-hmm. CSSH. Okay. The question was, have we used CSSH for small clusters? And I haven't. Can you educate us on that? Yeah.
It's a lot of fun if you have like 4 systems or 8 systems.
Mm-hmm.
If you type CSSH and then a list of host names, or an alias, which is a list of host names, you'll get a terminal pop up for each server, and then you get an extra terminal, and anything you type in that extra terminal goes into all the terminals. And so I wouldn't do it for too many, because you can type once, but you have to look at each one.
Right.
Yeah. So.
Yeah. Okay. But for small systems, that might be interesting. Mm-hmm. Yeah. There are other parallel tools. There's a parallel rsync, and I'm a great fan of rsync, and being able to do rsync in parallel to all of your systems at the same time, I think, is a great feature. Yeah. Mm-hmm. Okay, good. So thank you all for coming. Good set of questions, and I'll stay behind here for a few minutes. Thank you.
Citrix Zen Server gives you everything you need to integrate, manage, and automate a virtual data center, all on an enterprise-class, cloud-proven virtual platform, and at a third of the cost of other solutions. But why even bother with virtualizing your server infrastructure in the first place? Well, let's say you have a traditional one server to one application architecture, but you're running out of resources and performance is suffering. Once you order new server hardware, you'll wait for delivery, configure it, install your business application, stage and test the server, and finally, add it to your production farm. If you've been through this process before, you know it can take weeks or even months. You also know it's a manually intensive process that will burden your team every time you outgrow your current setup. With a virtual server solution, you could accomplish all of that in less than half a day. Server virtualization software separates the OS and application from the underlying server hardware. And with multiple virtual machines on a single server, you can use each of them to run different OSs and applications. This makes it possible to move your virtual machines from one piece of hardware to another whenever you want, to maximize utilization, simplify maintenance, or recover from a hardware failure, and without slowing down your applications or users. Clearly, server virtualization provides big benefits, and Citrix Zen Server provides even more. Since it's built on an open platform, Zen Server plays well with your existing hardware, storage systems, and IT management software, as well as with the industry's leading cloud service providers. Best of all, you can get started by downloading a fully functional, production-ready version of Zen Server for free. After a 10-minute installation process, you'll see how easy it is to start virtualizing your workloads and automating your IT management processes. And when you're ready for a richer set of management tools, just upgrade to one of the premium editions of Zen Server. So whether you're interested in virtualizing servers for the first time, expanding your server virtualization footprint, or moving server workloads to the cloud, download and install Zen Server today and see how it can help you simplify your IT environment. Citrix Zen Server. Do more. Don't spend more.
Your customers rely on your website or application. If it's slow or non-responsive, it infuriates your users and costs you money. Keeping your business-critical systems humming along requires insight into what they're doing. Your system metrics tell stories that can reveal performance bottlenecks, resource limitations, and other problems. But how do you keep an eye on all of your system's performance metrics in real time and record this data for later analysis? Enter Longview, the new way to see what's really going on under the hood. The Longview dashboard lets you visualize the status of all your systems, providing you with a bird's-eye view of your entire fleet. You can sort by CPU, memory, swap, processes load, and network usage. Click a specific system to access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding Longview to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to Longview. Then the graphs start rolling. Use Longview to gain visibility into your servers, so when your website or app heats up, it stays up.